ever seen a jet break the sound barrier? It's a pretty incredible sight. And that breaking of the sound barrier is possible because the speed of sound is a fixed speed as it travels through air. And that speed of sound is roughly 760 miles per hour in normal atmospheric conditions. But the speed of sound does not have a fixed speed. Instead, the speed of sound is completely determined by the material it's traveling through. We already said the speed of sound through air is roughly 760 miles per hour, which is ballpark 340 meters per second. In water, sound travels at roughly 5 times the speed it does in air, about 1,500 meters per second. In copper, like in a piano string, the speed of sound is even faster, traveling at close to 4,000 meters per second. The reason for the difference in the speed of sound in different materials lies in the difference in 2 important characteristics: stiffness and density. Generally speaking, compression waves, such as sound waves, don't travel well through a medium that's easily compressible. Here's a shot from an old commercial that demonstrates how soft and comfortable a mattress is. In the commercial, the gentleman drops the bowling ball onto the mattress. When the bowling ball hits the mattress compresses, absorbing the energy. The end result is that the energy created by the ball hitting the mattress is absorbed by the individual coil springs and not transferred to the bowling pins. So the bowling pins stay still. That's good for a mattress, but bad for sound. Soft, compressible materials absorb sound instead of transferring it. The density of the material also impacts how well sound travels. To see this difference, we can look at 2 different situations. First is someone running through water. If you run through water, it's difficult. It slows you down. But you create lots of waves, and those waves can travel a long distance. If you remember the big earthquake in Japan, the waves created in the ocean by the earthquake traveled a long ways. Eventually, they even hit the shore of Hawaii and California. However, it took several days for the waves to travel that far. So a dense medium has 2 effects. 1, the waves travel slower. But the energy is transferred very efficiently, so the waves travel a longer distance. If we contrast running through water with running through a field, the situation is completely different. In this picture of a dog running through a wheat field, the wheat field is not very dense. There's lots of open space between the wheat. As a result, the wheat field doesn't slow down the dog much at all. But the dog doesn't really create a lot of waves. He might shake the stems of wheat that are immediately next to him. But that energy, or the rustling of wheat, is not going to be transferred, or it's not going to create waves that ripple across the wheat field in the same way that when someone runs through water, it creates waves that can go on sometimes for miles and miles. So if the medium is not very dense, the sound waves travel faster, but they don't travel as far because the energy isn't transferred very efficiently. We call this loss of energy attenuation. Waves traveling in a dense material have a slow speed but a low attenuation, whereas waves traveling through material that is not very dense have a higher speed but also a higher attenuation. Sound intensity is a measurement of power, or the amount of energy transferred by the sound each second. We said in a previous video that the loudness of a sound is relative to its amplitude, but it's not a direct relation. There's actually a long, complicated equation that describes the relationship between intensity and amplitude, but it's not one you have to memorize. Instead, you simply need to know the relationship that the intensity, or the power produced, is proportional to the amplitude squared. So if you double your amplitude, you're actually going to quadruple your intensity, or the amount of energy transferred each second. The standard unit for measuring intensity is decibels. Decibels are a logarithmic function, where a 10 decibel increase means the sound has increased by 10-fold, and a 20 decibel increase means the sound has equaled by 100-fold. The easiest way to convert change in decibels to change in power is to focus on the tens unit and make that the exponent on the number 10. For example, if you had a 40 decibel increase, simply take the 4 in the tens position and then write the number 10, and then that 4 becomes the exponent on your 10. So a 40 decibel increase is actually a 10,000 times increase in power or intensity. Likewise, a 60 decibel increase, that would be equal to a 10 to the 6th increase in power, or 1 million times more power. Once we understand the relationship between decibels and power and amplitude, a problem such as this one should seem fairly easy. We have two sirens, a 30 decibel and a 10 decibel siren. That means the difference between the two is 20 decibels. To convert that to power, we simply take the 2, and that becomes the exponent on our 10. So a 20 decibel increase becomes a 100-fold increase in power. But the question isn't asking about power, it's asking about a change in amplitude. And you should recall that intensity is proportional to your amplitude squared. So if our intensity increases by 100-fold, we can write that as proportional to a squared. Square root both sides, and we get a is proportional to 10, meaning our amplitude has increased by 10-fold. This next question is testing our understanding of what causes sound to speed up or slow down. If you remember the picture of the man, if you remember the analogy of running through water versus running through a wheat field, you'll recall that density slows sound down. So density is definitely out. Since gas is compressible, any increase in pressure is going to relate to an increase in density. So if density is out, pressure is out. We haven't talked about temperature, so we could leave that as a maybe for now. Increasing the volume of gas would only matter if that in turn changed the density. If not, changing the volume doesn't change the speed of sound. So by elimination, we can hone in on temperature. And this is true. All things being equal, a higher temperature does mean that sound travels faster through the medium. That's true for gases, solids, and liquids. The reason that temperature increases the speed of sound in a medium is that temperature causes the molecules to move around faster. And as they move around faster, they bump into each other more frequently, which means they have more opportunities to collide and transfer energy.